Here's part 2 of the chemical reactions video dealing with balancing reactions and 5 basic types. And for part 2, it's going to be a matter of practice. So I have a few practice problems right here, and I'm just going to kind of go step by step through them so that especially if you have difficulty doing this, it'll help to watch. Okay, and you can kind of practice along or take notes as I go through this. Okay, for the first one, let's see, we have C7H14 as our reactant, and it breaks down to C7H8 and some hydrogen gas. Okay, so this is a decomposition reaction. I like to keep practicing that too. So decomposition reaction. But we want to balance it, right? Well, we already have 7 atoms of carbon on each side, but we have 14 hydrogens on the left. I'll just write that up here to make a note of it. And we have 8 here, and we only have 2 here. Since this one already has the 7 carbons just like we have on the left, we really need to address this hydrogen here. And so what could we multiply this by so that the total number of hydrogens on the right hand side of the arrow would equal 14? Okay, well 6 plus 8 gives us 14, huh? So if we multiply 3 times the 2 hydrogens to give us 6 here, then we'd have 6 plus 8. That gives us the 14 hydrogens on the right hand side, which is exactly what we have on the left. So double checking, we have 7 carbons on the left, 7 carbons on the right, 14 hydrogens on the left, and 14 hydrogens on the right. The balanced reaction is 1, 1, 3. So it's 1, 1, 3. Okay? Now to the next one. Here we have magnesium metal, so it's a solid, right? And let's say we put it in an aqueous solution. Some people say aqueous. AQ stands for aqueous. And so that means that this iron 3 chloride is dissolved in water. Notice that the iron ions here are of the +3 type because we have 3 chloride ions hooked on to the one iron 3 ion. And what do we get for products? We get MgCl2, or magnesium chloride, and we have iron, solid iron being formed. The magnesium chloride would be dissolved in water. I'll call it aqueous, or AQ there. Okay, what type of reaction is this? Think back. We have a single element here reacting with a 2-part compound. The magnesium, it's more active than the iron, so it hooks onto the chlorine instead of the iron. So that's a single displacement or single replacement reaction. Remember, that's the same thing as replacement. I tend to use them interchangeably. All right. We have 3 chlorines on the left, but only 2 on the right. So how do we deal with something like that? Well, we need to shoot for a common multiple, which is, that's right, 6. Okay, so what times 3 gives us 6 on this side? 2. So I'll multiply this term by 2. That means we have 2 times the 3 chlorines. That gives us 6 chlorines on the left. And what times 2 gives us 6? That's right, 3. So I'll put the multiplier of 3 in front of MgCl2. 3 times 2 gives us 6 chlorines on the right. So our chlorines are now balanced on each side. What does that do to everything else? Well, 2 irons here, and we only have 1 on this side, so I'm going to need to multiply this iron, or Fe, by 2. Alright? We have 3 Mgs on the right-hand side. We're going to need 3 Mgs on the left, so I'm going to multiply this Mg on the left by 3. So the final balanced equation is 3, 2, 3, 2. Let's go to the third one. What kind of reaction is this? we have two items combining to form one. Well, that must mean it's a synthesis type of reaction, or a combining type of reaction. Let's balance it out. We have 2 oxygens on the left and 3 on the right, so we need to shoot for the common multiple of 6 again in this case. So I'll multiply this oxygen, this O2 by 3. 3 times 2 gives us 6. I'll multiply this by 2. 2 times 3 gives us 6 oxygens. So we have 6 O2s on 6 oxygens on each side, not 6 O2s. We have 2 times 2 is 4 irons on the right, but only 1 iron on the left. So I'm going to need to multiply this one on the left by 4, so that we have 4 irons over here. So it's balanced now. We have 4 Fe's reacting with 3 oxygens to produce 2 Fe2O3s. Next one. Here we have this one substance on the left breaking down into 3 substances on the right. That is definitely decomposition. But notice in this case, instead of breaking into 2 things, it's breaking up into 3. So how are we going to balance this out? Notice on the right we have carbon here in the CO2 and carbon here in Na2CO3. So we have carbon in both of these compounds in the product side. So how do we balance this out? Let's see here. Well, we have we can try fixing the sodiums. Let's do that. We have 2 sodiums on the on the right, excuse me. So I need to balance that out and have 2 sodiums on the left. I'll multiply NaHCO3 by 2, and that'll give me 2 NAs on the left. So the sodium is balanced. Let's see what that does to everything else. That means that we have 2 times 1 or 2 hydrogens, which is what we have on the right. That's good. We have 2 times 1 carbon or 2 carbons, and we have 1 plus 1 is 2 carbons. That's good. We have 2 times 3 or 6 oxygens. How many oxygens do we have on the right? We have 2, and 1 is 3, and 3 more makes 6. Good, we're done. So the balancing only required us to put a multiplier of 2, or a coefficient of 2, in front of this first term, and everything else is understood just to have a 1 in front of it. But we, of course, don't write the 1s down, do we? Uh-oh. What do we do with these? No products are written out. That means we're going to have to think a little bit, huh? And in this final one, the products are written out, but no reactants are written. So how do we do that? Well, you know about the 5 basic types of reactions, so that'll be a big help if you think about what type of reaction it is, or what you make a hypothesis. What type of reaction do you think this is going to be, based on the fact that we have a metal here hooked onto a nonmetal, reacting with another metal, nonmetal compound? Think about it. Is it synthesis, decomposition, single replacement, double replacement, or combustion? Well, I think you have the idea. It's going to be a double replacement probably, huh? So the silver is going to go over and hook onto the chloride ion, and the calcium would go over and hook on to the nonmetal NO3. A double switch. So based on our hypothesis, let's write out our probable products. So if the silver goes over and hooks onto the Cl's, we'd end up with AgCl. Don't write Cl2. We have to check that later. Let's just write our skeleton products down first, and then check the charges to make sure that they add up to 0. That's a very important step. What's the other skeleton compound produced? Okay, well, we'd have calcium as the metal, so remember, metals are written as the first term, hooking onto the NO3, which is the nonmetal. That would be the second term. Remember, metal first, nonmetal second. Metal, nonmetal, metal, nonmetal, and so forth. Okay, so now what do we do? Well, we need to look and see if these products, these compounds on the product side, are written correctly so that each compound is neutral. If you look at the periodic table, and you should always have your periodic table handy, we see the chlorine is a halogen, and it has a charge then, since it's a halogen, its typical charge is -1 when it forms an ion. We look up silver, we find that it only has one charge, and that's a +1 when it forms an ion. So this is good. +1 and -1 add up to 0. That means that we do not have to write any subscripts for this. We don't write a 2 next to the chlorine, do we? We only need one chloride. So AgCl is correct. Okay, now let's check the correctness of CaNO3. Is this a neutral compound? Well, calcium, if you look it up, it's an alkaline earth metal. So it must, when it forms an ion, be a +2, have a +2 charge. The nitrate, if you look on your polyatomic ion sheet, has a -1 charge for this, doesn't it? Well, a -1 added to a +2 does not equal 0, does it? So we're going to have to increase the number of NO3s, or this nitrate polyatomic ion. So let's put parentheses around the NO3 and double it. Now we can't put a 2 in front to do that. We're just trying to change the chemical formula, not how many of the chemical formula. So we'll put a little 2 as a subscript right there. There. Now with that, we have 2 of these NO3s hooked on to one of the calcium atoms. So it's CaNO3 2. This is now the correct chemical formula. When you add up the charges, they add up to 0. Now that the chemical formulas are written correctly, then we can go ahead and balance the reaction. Okay, so what do we have? Let's check the silvers. We have 1 silver on the left, 1 on the right. Don't confuse the numbers I'm putting here with the charges. I'm just counting atoms now. How about NO3s on the left? We only have 1 NO3 on the left, but we have 2 on the right. So we need to double that, huh? So let's put a 2 in front here. Now that gives us 2 silvers and 2 NO3s. So the NO3s are balanced on each side. We have 2 NO3s on the left, 2 NO3s on the right. Problem is now we have 2 silvers on the left, 2 Ags on the left, but only 1 Ag on the right. So that means I'm going to need to double the number of AgCls on the right. Now we end up with 2 Ags on the right. In doing that, though, I also doubled the number of chlorines. Well, we have 2 chlorines on the right. But that's good because we have 2 chlorines on the left originally. We have 1 calcium on the left. We have 1 calcium on the right. So it turns out then that the balanced equation is a 2-1-2-1 equation. 2 AgNO3s react with 1 calcium chloride to produce 2 AgCls and 1 calcium nitrate. Next problem. Here we have the reactants written out, but no products again. So we need to think, what type of reaction would this be? Whereas the one before was a double replacement reaction, I'll just put DR for short. What would this one be? Here we have a single element reacting with a 2-part compound. Could it be that this would be a single replacement reaction or displacement reaction? Let's check our guess and write out the products based on that hypothesis. Well, if that hypothesis of single replacement reaction is true, then the aluminum is going to go over and take the place of the copper and hook onto the sulfate. So we'd end up with AlSO4. AlSO4, and that would leave the copper, the Cu, left out in the cold. Okay? Before we balance the reaction, though, we need to check for the accuracy of the compound. Is the compound correct? AlSO4. So we look up SO4, which is a sulfate ion, on our polyatomic ion sheet, and it has a -2 charge. What about aluminum? Aluminum, if you look on your periodic table, it has a +3 charge. Well, +3 and -2 does not add up to 0, does it? So we're going to need to shoot for a common multiple. And what would that be? Think. Common multiple, 3 and 2, that's right, 6. So what times a +3 gives us 6? +6? 2. So I'll put a little 2 here as a subscript next to the aluminum. 2 times a +3 gives us a +6. And I'm going to put parentheses around the SO4. What times a -2 gives us -6? 3. So the correct compound is Al2SO4 3. So that means we have 2 aluminums at +3 apiece, and we have 3 sulfates at -2 apiece. So that gives us a +6 and a -6, and that adds up to 0. Okay? Now the copper, since it's by itself, it's just a neutral compound. It has a charge of 0. And we don't have to worry about that one. That's just the solid copper being formed. Okay, now we're ready to balance. So let's see, we have 2 aluminums on the right-hand side, so we're going to need to have 2 aluminums on the left. I'll go ahead and multiply the aluminums on the left by 2. We have 3 sulfates on the right-hand side here. See, that little 3 refers to everything in the parentheses. So I'm going to need to multiply CuSO4 by 3 so that I can have 3 sulfates on the left. What does that do to my copper? Well, I put a 3 in front of this whole term here, so that also means we have 3 coppers on the left. And if that's true, then I need to multiply the copper on the right by 3. So what we end up with is 2 aluminums react with 3 copper, 2 sulfates to produce 1 formula unit of aluminum sulfate and 3 copper atoms. Last one. No, I'm sorry, we have 2 more to go. Ready? We have another situation where we don't have products written. So think, what kind of reaction would this be? Single replacement, double replacement, synthesis, decomposition, combustion. Think, what could it be? Well, here's a non-metal, bromine. Bromine is actually a liquid at room temperature, but it occurs as pairs of bromine atoms. And then here we have iron 3 iodide. Okay, well, remember this iron is the metal, and here we have the iodides, which are the non-metal. So if we had this bromine, and bromine happens to be more reactive than iodine because it's higher up on the periodic table than iodine is. It's more reactive. It can pull the electron, it can grab electrons more strongly than iodine. That means that bromine probably will take the place of the iodine there. So that means a possible single replacement reaction. Let's try that hypothesis. That's our guess. Now let's see how it works. So if bromine replaces the iodine, then we're going to end up with the iron hooked onto bromine instead of iodine. Okay, I'm not going to put a 2 there. I'm just going to leave it as a skeleton right now, and then we'll address that in a minute. Okay, what else would happen? Well, we have the iodine left out in the cold. Alright, now let's see if FeBr is the correctly written chemical formula. Fe, in this example, had a +3 charge, and we could tell that because it hooked on to 3 iodines. So my hypothesis is that it's probably a +3 on this side too then. If it wasn't, I mean, that could happen, but we would end up with what's called an oxidation-reduction reaction. And, well, we still have an oxidation-reduction reaction here, but we need to wait and learn about other ways to classify reactions. So I'm not even going to bring oxidation-reduction reaction up at this point. But let's just say the iron is a +3. Bromine has a -3 charge. It's a halogen, so we're going to assume that. So we need 3 bromines at -1 apiece, so that when it adds to the +3 of the iron, it adds up to 0. So I'll put a little 3 as a subscript to the right of the Br. So it's FeBr3. That is the correct chemical formula there. Iodine, just like fluorine, chlorine, bromine, and so on, it comes in usually in pairs. Okay, so I'm going to put I2 down, and that would be a solid actually, but I'm not really concerned right now about what phase of matter they're in. Okay, so anyway, FeBr3 plus I2. Now let's go ahead and, since these are written correctly now, this is the correct chemical formula, now we can go ahead and balance. 3 Brs on the right, only 2 on the left. How do we fix? Let's shoot for a common multiple of 6 in this case. So I'll multiply this one by 3. 3 times 2 is 6. And I'll multiply this term by 2. 2 times 3 is 6. So we have 6 bromines on the left, 6 bromines on the right. Bromines are fixed. Let's look at the iodines. Here we have 2 iodines on the right and 3 on the left. Let's go ahead and shoot for a common multiple. I'll multiply this by 3. 3 times 2 is 6 iodines. I'll multiply this by 2. 2 times 3 is 6 iodines. Okay, what is that? Let's check the irons to make sure that that's balanced. 2 Fe's on the left, 2 Fe's on the right. So we're good. So the balanced reaction is 2, 3, 2, 3. Now we're on the last one. The last one doesn't have any reactants listed. It just has products. So let's think, what possible type of reaction could this be? Well, we have a single element over here produced, and we have a 2-part compound here that's produced. So I wonder if it's the result of a single replacement again. Single replacement reaction. Well, let's see. Let's just work backwards. We have copper by itself on the left, and we'd have the silver hooked on to the NO3 on the left. That would work, right? Copper taking the place of the silver. Now let's check to make sure that the chemical formula is written correctly. Silver, if you look up on the period table, has a +1 charge. Look up the nitrate, a polyatomic ion. On your polyatomic ion sheet, it has a -1 charge. +1, -1, add to 0. We don't need to mess with this. This is the correct chemical formula, AgNO3. So aren't you glad I didn't put a little 2 next to the NO3 here like there was on this side? There was no need. In fact, it would make it wrong. Copper's by itself. It's a solid. It's fine the way it is. No charge to it. Just like silver's by itself on this side. Okay, so now that we know that the chemicals are written correctly, now we can go ahead and balance if needed. We have 1 Ag on the left, 1 on the right. That's balanced. We have 1 NO3 on the left, but we have 2 NO3s on the right. I'm going to need to double this over here. That changes the number of silvers though, huh? So I'm going to have to go to this side and double the number of silvers. How about our coppers? Are we okay? Yeah, 1 copper on the left, 1 copper on the right. We're done. Thank you, everybody.